I'm a statistician from UCL Department of Statistical Science. This is actually my first appearance, and even these are my first minutes at PyData. And let's see whether what I have for you here is targeted at the right audience. I'm not so sure about that, but let's see. The most important thing I want to talk about is basically how to think about cluster analysis. And probably you were attracted by the title, right? So chances are I may not have to tell many of you what cluster analysis actually is, but still, because I don't know what your background is, I will give a short introduction to cluster analysis. So generally, cluster analysis is about finding groups in data. What you see here is you see a four-dimensional data set. All the objects in this data sets are actually Bs. So they are tetragonal Bs. And these four variables that you see here, they represent some genetic information about the Bs. And the idea is that because of this, using this genetic information, one could find species of these Bs. And that would basically mean we try to group these Bs into some groups. You see some groups already here on the screen. And there are actually lots of different methods to do this. I will quickly run through some of them. So the probably most well-known method for cluster analysis is k-means. So the idea is we basically try to group the objects in a data set that are represented by some p-dimensional, so here four-dimensional Euclidean points, in such a way that this sum is minimum, which basically means we assign every point to the mean of the cluster to which it is assigned. I should probably use this in order to show you this, so that's also over there. We try to assign them in such a way that this sum of squares is a minimum. That means that we represent basically all the objects in a cluster by some kind of centroid, which here is the mean vector. And this will give us basically compact clusters because the objects spread in all directions around the mean, and in all directions the distance is computed in the same way. There are some versions of this. One version is that we don't use squares here. Another version is that instead of the mean, we use some object in the data set, and then you would get a method that is called partitioning around medoids. And this is what it does on the Bs data. When looking at a plot like this, you always need to keep in mind these are the first two dimensions of a data set that is actually four-dimensional. So you don't see all the information here. If something looks a bit strange, then that could be an explanation of that. One thing you see is that, to some extent at least, all the clusters that are produced here are somewhat compact, right? So they are all more or less the same size. And they all spread in the same way in all directions. Okay, then a different approach, model-based approach, is we could fit a Gaussian mixture model to the data. So this actually goes back to 1894. You could say it's the oldest cluster analysis method there is, although Pearson didn't use it for cluster analysis. And the idea is we fit a model like this where we have proportions for every cluster. That's the parameters pi j here. And we model every single cluster by a Gaussian or normal distribution with a mean vector aj covariance matrix sigma j. And then we can assign the points after we estimated, for example, by maximum likelihood, all these parameters. In this method, the clusters are described by Gaussian distribution. So we get roughly elliptical clusters, and they have flexible size and shape. And how this looks like is this. And one thing that you particularly see here, I remind you again, right? Some of this looks somewhat weird, but we only see 2 dimensions out of 4. So there may be something going on in the other dimensions that explains this. One thing is you see this cluster number 5 here that has a much larger spread and spreads around number 8, which has a much smaller spread. This kind of stuff you can do with Gaussian mixtures, with flexible covariance matrices. You cannot have this with k-means. Okay, and then there are a number of completely different approaches to cluster analysis. Namely, approaches that operate on dissimilarity matrix. So you start this computing the dissimilarity measure for every pair of observations first. This could be the standard Euclidean distance, which I've used for this data set, but it could also be tailor-made distances for other data formats. Oh, I told you something wrong. Actually, for this data set, I used the tailor-made distance for another data format, and I will show you how this looks like. Generally, what we try to find here is we try to find a collection of similar objects which are dissimilar to all the objects that are not in the same cluster. Now, so actually, what is underlying the data is some genetic information that looks like this. So we basically have 236 tetragonal bees here, and they are characterized by 13 pairs of alleles. And these pairs of alleles are characterized by some genotypes that have some more or less arbitrary names. So that is actually behind the data set you saw before. And then you can define a distance between any pair of these bees here. And that gives you a distance matrix like this. So the information you have here is for every pair of bees, so this is between B1 and B2, measure how dissimilar they are. The four-dimensional data set you saw before is actually some kind of Euclidean approximation of this thing, which was generated by multidimensional scaling. I will tell you a lot of details, and I hope you take it in the right way, right? If you don't understand what this is already, you don't have to understand it afterwards. I will give you an overview what kind of stuff can be possible. Some things you are going to understand afterwards, but you pick the ones you want, right? Okay, so now that we have a dissimilarity method, we can compute classical hierarchical clustering methods. And the idea here is that you start from the lowest level at which every single observation is a cluster. So we have 236 clusters, which are all the observations. And then we merge the two most similar observations. I think that's going on somewhere down here. And then you have 235 clusters, right? One with two observations merged. And then you go up the hierarchy here. At every stage, you join the two most similar clusters. You put them together, so you have one fewer cluster, until at the end, everything is merged together in only one cluster. So you basically have a sequence of different clusterings with all numbers of clusters you can imagine. If you want to have a specific partitioning, you have to cut the hierarchy at a certain point, right? Here, for example, that gives you a partition. And the most frequently used hierarchical methods are single linkage, complete linkage, and average linkage, and they are defined by different ways of defining what the difference between two clusters is. So, for example, single linkage takes the minimum of all objects in the first set and all objects in the second set of the distances between these objects. Complete linkage takes the maximum. Average linkage takes the average. This goes back to 1951, SK means. Well, actually, these are the first things that were really intended to be cluster analysis methods. These can deliver quite different clusterings. Actually, complete linkage make sure that all dissimilarities within a cluster are small, whereas single linkage basically focuses on keeping the dissimilarities between clusters large. So these could be very compact. Those from single linkage will be well separated, but may be spread very widely. Okay, few more recent methods, spectral clustering. Basically, you do k-means, but after you have projected the data based on dissimilarities with some kind of fancy nonlinear dimension reduction method, right? You can make out that you are not meant to understand this if you don't understand already. But this is what you get from it. It's also different from k-means, has actually the possibility to put together a string of observations that may be widespread, but may belong together in a certain way. And then there are also density-based methods. So the idea here is that you want to identify clusters with modes in the density with areas where the density is high. One of these methods is dbScan from 1996. And the idea is you join all observations with neighboring points if they are close enough, and then you join neighborhoods if they share enough points. And that gives you again something special, namely the points that are denoted n here. It will only merge things where the density is high enough. Where the density is low, it will not put objects into any cluster. These are denoted by n here. And again, you see some in the middle of this, but they are very different in the other two dimensions. Okay, there are lots of other issues in cluster analysis. We may be interested in estimating the number of clusters. What does that say?
Just curious about these different algorithms.
Ah, okay, good.
Which of them require kind of a distance measure where the triangle inequality applies, or it's actually a Euclidean one, and which can you just have a non-Euclidean distance measure?
Ah, okay. In principle, none of these methods requires the triangle inequality to be fulfilled. However, some basically implicitly act as if, so in some the implicit logic would actually apply this. So you can, in principle, feed a non-Euclidean and non-metric dissimilarity measure in all of these. However, you may not, particularly when talking about density-based methods, you may not get a result that is very sensible. Yeah. Okay, so this is actually one issue I wanted to measure, dissimilarity definition. Oh, I didn't know about the normal stuff in this conference. Ask questions if you want. Of course, then I will overrun the half hour, but whether we have them in the middle or whether we have them in the end, I personally don't mind much. So perhaps it's better to ask questions on the fly. Good. So we could be interested in estimating the number of clusters. Certainly all of these methods give clusters, but it's not really clear in many situations whether there are actually clusters. So we are interested in validating them. And of course, we are interested in what kind of dissimilarity should we take and what kind of method should we take in a specific application. And that's what the talk mainly is about. So I'm now talking, and basically for the rest of the presentation, about benchmarking and measurement of quality in cluster analysis. And this all boils down to the question, you have a data set, you have different methods giving you different results, and the question is which clustering is better. So this is a clustering that is produced by a Gaussian mixture model on a data set. All of these points here are eruptions of the old faithful geyser geyser in the Yellowstone National Park, and the two dimensions here are standardized waiting time before this eruption and then the duration of the eruption. And this is by partitioning around medoids. So if you just look at this, let's call this number 1, let's call this number 2, let's have a bit of a vote. What do you think is actually better? Who likes the clustering number 1, which is this here, more? Okay, that's about, but you can see it, right? You can see that some points here are red, and so the difference is some points here are red, right? And these are black here. So that's basically, the colors are the clusters. Okay, we have something like 18 votes for number 1. Who thinks number 2 is better? A few, okay, 4 or 5, good. We will see later in the presentation whether the measurements that I show you will reproduce this. Second thing, this is actually an artificial data set that I generated to highlight a certain issue. So this is number 1, this is number 2. This was generated by having a uniform distribution here and 2 Gaussians here. So number 1, number 2. Who likes number 1 more? Okay, that's 7. Who likes number 2 more? Okay, that is about 21. Good. So I wanted to highlight one thing with this example, which is that when you do clustering, you may actually be interested in different things. So you may be interested, for example, in capturing some kind of intuitive shapes that you see here, in which case the second clustering would be preferable, or you may be interested in having all small distances within clusters, so that all the objects within a cluster are similar to each other, in which case this here would be quite problematic, right? Because there are very huge distances within this clustering. Okay, now what do we do in order to compare different cluster analysis methods? I will come back to both of these datasets later. We could use real datasets with known classes, so basically supervised classification datasets. We could use simulated datasets from mixture distributions where we know the truth because we basically put it in. Or we could use real datasets without known classes. Now you will think about why would one think about the last, because we want to, if we know the truth, we actually can compute misclassification rates, so that would be easy then to compare clusterings. However, there are some disadvantages of benchmarking with known truth. Namely, in datasets with known classes, clustering is actually not of real scientific interest, right? Why would we want to find the classes that we already know? Because of this, they actually deviate systematically from real clustering problems, unless you find somewhere in the beginning, at some point in time, these classes were indeed not known. But that's not the typical situation for these data sets.
But that's not true if you manually label some of your unlabeled data, a great effort, for instance.
Well, yeah. So you may be in a situation where you actually do not know the true classes of most of the points, and you can find out the true classes of some if you put great effort in. Yeah, okay, that's good. I mean, I should say, this appears on a later slide, I'm not going to tell you that I'm against doing this, right? There are a number of situations in which this actually makes sense. But I'm basically going to advertise that we should also use datasets without known classes. So indeed, there are situations where this makes sense. So, however, the fact that we know certain true classes doesn't preclude other legitimate or true clusterings, right? So if you know a certain clustering on the dataset and a method finds you another one, it may be that this other one makes sense, right? And would then not be a fair thing to discard the other method because you learned something interesting about the dataset from the other method that you didn't know before. And also, classes in supervised classification problems may not qualify as data analytic clusters, so you may not expect a clustering method to find them. So in summary, there could be better truths than the truth we actually know. And I give you an example for this. This is a data set from social stratification that we analyzed in 2013. This is principal components of a data set that originally I think was 13-dimensional. Every object here is a person in the United States, characterized by variables such as income, number of savings account, house ownership, and things like this. Now, for this data set, we had some true classes, and these were standard occupation classes, such as manual workers, managerials, and professionals not working, 7 of them. Here are the colors. This is how this looks like in the principal component plot, and you even can try to find some kind of plot that optimally separates these known classes from each other. Which way ever you look through the data set, you get to the conclusion that these classes are actually not data analytic clusters. They don't look anywhere near what you think what a cluster is. They are not well separated, so you cannot expect any clustering method to find it. Similar problem is if you generate data from mixture distributions. So if I wouldn't give you the numbers of clusters here in this data set and you would look at it, probably hardly anyone would guess that the number of clusters in this data set is 5, right? Because this is from a mixture of 5 Gaussian distributions, but these are arranged in such a way that they are not really separated from each other. Okay, so I mean, using a known truth is useful and fair enough, so I agree with the guy in front here. But also we want to evaluate clustering on data for which the truth is not known. And this is what I'm talking about now. Actually, there is some stuff about this already in the literature. There's a range of cluster validation indexes measuring clustering quality. One of the most prominent ones is the average silhouette width, introduced in 1990 by Kaufman and Rosseo. The idea of this is as follows. So you compute this thing, which is called the silhouette width, for every observation. And the A for every observation is the average distance to points in its own cluster. So you have a clustering, right? You want to evaluate its quality. And the B, here you compute the average distance of the object xi to all the objects in another cluster to which it's not assigned, and the minimum here makes sure it's the closest one, so the one that is the best other candidate to assign this point to. Now, if this object sits very comfortably in its own cluster, the BIC should be much larger than the AIC, right? The point should be very close to the observations in its own cluster, and then this would be positive. And this intuition is used for saying a good clustering is a clustering where the average of these silhouette width values is large. Now, generally, not only this index, but all the other cluster validity indexes have some kind of one-size-fits-all approach, right? You have one number that gives you the quality for a clustering. And in a situation like this, where you have very large distances within a cluster here, usually these indexes, including the ASW, will be dominated by trying to get homogeneous clusters. So pretty much all of these will pick this before this, which of course does not agree with the majority of the people in the room here. So actually, I think there is some kind of wrong philosophy behind this. Because, so my general philosophy is there are various different aims of clustering, and in different applications you may be interested in different things. And I would want to measure them separately to characterize what a method does best instead of summarizing everything in a single number. And here is a list of typical clustering aims. So you could be interested in clusters that are well separated from each other, in clusters that are very homogeneous in the sense of having low within cluster distances. You could be interested in clusters that can be modeled by homogeneous distributional shapes like the Gaussian or the uniform distribution. You could be interested in having a good representation of your data by centroids. You could be interested in having little loss of information of the original distance by putting them in clusters. You can actually measure this by defining a cluster-based distance that assigns a distance of 1 between any 2 points that are in different clusters and 0 for 2 points in the same cluster. You could be interested in clusters that are regions of high density within cluster gaps. You could be interested in uniform cluster sizes, and some applications having extremely small and extremely large ones just doesn't make much sense. And you could be interested in stability. So if you basically shift the observations around a bit, you want to have something very similar. Now, actually, one thing to realize is that these aims may be in conflict with each other, for which reason I created this data set, right? So if you want to have small within cluster distances, this gives you something different from having kind of homogeneous distributional shapes within clusters, in which case you don't want to have the first one, but the second. So in a given application, you got to decide what you want. And for example, if you want to do pattern recognition in images, separation of your clusters is very important. If you want to do clustering for information reduction and you want to represent all your objects in one cluster by a centroid, this is the most important thing that you could be interested in. If you want to find groups in social network analysis, you don't want to have large within cluster gaps, because then that's not a group anymore. And in some applications, you actually want to find some underlying true classes for which there is a scientific model that describes how these classes came about, like, for example, in biological species. Okay, so I'm now talking about several statistics that measure different aspects of quality in clustering. And the first one I'm going to talk about is measuring between cluster separation. There are several ways of doing this. Unfortunately, not only are there several possible clustering aims, there are also several ways of approaching each single one. And there are some straightforward ideas. One idea is, let's say we want to look at the black and the red cluster here, to take basically the minimum distance between any two objects of different clusters. That would give you this. Or you could say, we are interested in how far the means of the clusters are away from each other. Now, actually, these two give you quite different concepts of separation. So the minimum distance relies only on 2 points, and the centroid distance ignores what goes on at the border between the clusters, so in here. So basically, both of these are kind of extreme, and I wanted to come up with a compromise between them. So this I call p-separation index. Here I look at the 10% points in any cluster that are closest to the other cluster, by which I mean have the minimum distance to their closest point in the other cluster. And then I compute the average distance of these, and that gives me a separation index. So here that would be the points that are marked by crosses. Okay, something else, measuring density mountains versus valleys. So whether a clustering captures the idea that in a cluster the density is high, between the cluster the density is low. There are two aspects of this. The first one is we want the density to go down from the mode, not up, and we want no gaps or valleys, so where the density goes down and then up again within the same cluster. And the other one is we want that the cluster borders are basically valleys, so the cluster borders don't run through density mountains. I base this on some kind of kernel density which can be computed from dissimilarities, and the principle is the following. So if you compute this, here the thicker points are those that have a higher density. It's the same data set as before. Now, I'm going to show this as an example with a quite weird clustering. This is the single linkage clustering with two clusters. One cluster is this point alone, and the other cluster is all these. You may not find this particularly convincing, but I use this because I want to show you how this density index for the bigger cluster is actually computed. So what I do is I start from the point with the biggest density, which is somewhere in here. I magnify this bit now. And then I go to its nearest point, and I add a penalty if the density then goes up, which in the first step it can't, right? Because I start from the mode. I go further. Always I go for the closest point to what is already connected, and I add a penalty if the density is up, but none, and we collect these penalty, none if the density goes down. So at some point, the density will go down. So this is red. Whenever there's red, there's a penalty. So now we go through here, right? This is the process. And at some point, we will be in a situation where we have a very low density, and we will go somewhere where the density is high again, and that adds a huge penalty. So this is what I basically do in order to measure that this is not a good cluster. We have gone very far down, and suddenly we go up again, right? And then the whole thing goes on, and we have another fairly big penalty here, and we have a little bit of a penalty here. And then there are some other further penalties that are added for high density points for which a large amount of the density comes from another cluster. What you see here is you see a different clustering, right? This is a 3-cluster solution from a density-based method, and there these two are separated clusterings, and we have some penalty here because there's a high density, and in their neighborhoods there are points with from another cluster. Okay, there are lots of other statistics we could be interested in. We could be interested in the within cluster average distance. We could be interested in within cluster similarity measure that specifies the distance from the shape to, for example, a Gaussian or uniform distribution, whatever we are interested in. We could be interested in the within cluster squared distance to centroid. If you only are interested in this, you should do k-means, because this is what k-means does best. We could be interested in a correlation coefficient that compares the distance that we originally had with the distance that is defined by the clusterings to see how much information loss we have. We could look at the entropy of cluster sizes. We could look at the average largest within cluster gap. And we could, for assessing stability, look at the variation of clusterings on bootstrapped data sets. And that gives us a multidimensional characterization of cluster qualities. And then we standardize all indexes to the range 0, 1 in such a way that large is good. So the numbers I will show you from now on are always to be interpreted in this manner. The large is good. So here are some examples. This is the data set, the artificial data set from before. So here you see actually that this data set is better in one respect, namely the average within cluster dissimilarity. If you want to keep that low, you better go for this one. Whereas in the other respects, particularly separation, because there's a huge separation here, and these two are okay relative to their sizes, and not having a within cluster gap, this one is actually better. So you basically see in which sense one is better, in which sense the other one is better. These are 6 clusterings on the old faithful Geyser data. This is from a Gaussian mixture model with 2 clusters. This is partitioning around medoids. This is spectral clustering. This is average linkage cut so that we get 2 clusters. This is the weird one you saw before, single linkage with 2 clusters. And this is a density-based clustering with 3. And then, of course, again, you can compute lots of things. I will only very quickly comment on some. So the PAM clustering is this one, which looks a bit weird, right, from the points here. And you see that this is actually fairly good when it comes to average within cluster distances. But regarding most other criteria, this is worse than the one you get from mclust and many others here. Then the strange single linkage clustering is pretty good in some respects. So for example, the separation, right, has a very good separation because this cluster here is as well separated as possible in the data set from the rest. Whereas it's pretty bad regarding some other criteria, like average within cluster distance. It's not particularly good, as I showed you before. When it comes to the density index, the representation of the information of the dissimilarities in the clustering is also quite bad. And here what you should expect, the one from the Gaussian mixture is best when it comes to normality, normal distributional shapes of the clusters. All the others don't do such a good job on this. You can also plot this, right? For example, if you want to look at the density index and you now may be interested in all these methods over several different numbers of clusters, you realize, okay, mclust was the best for 2 clusters, but you have some other methods that give very good results for higher numbers of clusters. Yeah, and then I'm very close to the end. So the main message here is that the clustering quality is multidimensional. What I want to have is I want to have a multidimensional evaluation clustering a method's behavior. If you still want to have a single value, if you apply clustering to a specific data set, you can compute a weighted mean. What you need to think about is how important which aspect of clustering is to you. Because that comes from the application, right? The statistics cannot decide that. This can be used for benchmarking, comparing different clustering methods without known truth. But of course, which is something you may be more interested in, this can also be used if you just have your own data set to cluster and you want to know in what way different methods cluster these data. What is required, and I didn't really talk about that, is you need some kind of standardization that makes different indexes and number of clusters comparable. Much of this is implemented in the R package FPC, but not all. I'm not sure whether that's a wise decision, right? I'm talking about current research that is going on. So I'm not talking about a fancy package that already can do all these things in a particularly user-friendly way. That's what you get when you invite scientists from university.
It's not Python.
Sorry?
It's not Python.
And it's not in Python, but nobody told me I should do something in Python. I actually never used Python. Okay, no. I didn't think, when they asked me to present here, I think they didn't want me to say this, but nobody warned me again, so I just did it. What we also do, a group of people where my name is in it, but not in the first place, this is the international, these are some people from the International Federation of Classification Society, and we want to set up a cluster benchmarking repository with some data sets that can be used for benchmarking. And the different thing between this and things that you already know, like machine learning repository UCI and stuff, is that we want to have them documented in such a way that you can actually, from the information, get what kind of clustering you may want there. The work is supported by EPSRC, and I also want to do a little bit of marketing. So this came out in December 2015. It's a wonderful book. You should give it to all your friends and family because they will all love it. And yeah, so that's it. Thank you very much. Okay, lots of questions. I think the first one I saw was here. Is it actually something the chair should do? Should I do that?
Yes, this is fine.
Okay, good.
I wanted to ask if you used any of these algorithms to look where there's missing data. Is there a process that you would use to try and work out the best clusters for when you have an incomplete data set or bad data?
So, what is this? Yeah, okay. So I was asked what to do in case of missing data. Now actually, I personally, so I haven't involved missing data in the research that I'm doing right now, but the thing is that missing data from my point of view would be handled first by the clustering method. So the question there is, for example, how to design a dissimilarity measure in case of missing values. And there are several approaches, like, for example, if you have categorical variables, you can make it another category, or you can tweak the formula in such a way that missing data are weighted out and things like this. But it doesn't directly feature in my research right now. Okay, yeah?
How does the indexing method lead you to try and decide what's the right number of clusters?
I'm working on that. The thing is that, like the question which the best clustering is, also, well, the number of clusters is, he asked for how can these be used to find the right number of clusters. So also in this respect, it is very important what is required in an application. So the rough answer I can give to that is basically if you know the weights that the different criteria should have in your application, of course, you can piece together a single index, and then you can, of course, use it to compare different numbers of clusters. There are some details about how exactly to make them comparable, on which I'm working. But I mean, if you can come up with one weighting right away, that's what you have. Yes, please.
I have a question, because I often, if I look at the data set, and I have very different categorical, well, sometimes categorical data, sometimes linear data, I have no idea how to make a similarity definition, how to actually start even clustering, because I don't know how to relate the different dimensions I have. Can you?
So the key thing about this is mixed types of variables, right? So you have categorical variables, you have continuous variables. Actually, in this paper, let me bring this up again, where we analyzed the social stratification data, this one. This is a reference that I can give. Part of this paper is a discussion how to do this, and there is a certain scheme. So it requires you to think about how different, comparing with continuous data, two categories in your categorical data should be. And one possibility that we explored there is to think about the variance, the contribution to the variance of the overall distance that you get from your categorical data if you code it as dummies. And then you can put a weight in there that makes sure that this has the same contribution to the variation than a continuous variable. But there are a number of detailed discussions on this in this paper. I think if you Google Hennig and Liao 2013, you may find that. Further questions? I'm not responsible for timekeeping here, right? That's up to the chair. Okay, good. Yes, please.
Thank you. So how do you basically how do you decide in multiple dimensions what sort of clustering you want?
Well, really, the first thing is I think about what specific application this is, so what the requirements are. I think there's a basic distinction that I would want to make first, which I call the distinction between constructive and realist clustering. So a typical problem is where you would usually use something like k-means is that you are not really interested in finding density values and making the statement, okay, there are some two different groups. You just want to reduce information so that you can handle the data in a better way. And in such applications, you usually want to have things like small within cluster dissimilarities, and you want often also a good representation by centroids, and that would lead you to methods like k-means, complete linkage, and so on. Or on the other hand, if you want to have something that feels like belonging together, where you could kind of postulate there's some underlying thing going on that produces particular shapes, you would rather go either in the direction of having a mixture model, if you have some idea how you would want to model this statistically, or in the direction of methods that focus much more on separation, such as spectral clustering, for example. So that would be the rough thing. But of course, if I think like this, I can also use the criteria, run lots of different ones, and see what the criteria give. Okay, more, please. Yeah, yes, please.
So if you wanted to say clustering which was robust to outliers, is that something you would handle at a pre-processing step?
No, well, I actually, I took this out of this presentation, but I've actually worked on this. I'm currently thinking about how to involve outliers and noise in these criteria. However, also there are clustering methods that are designed in such a way that they are more robust to outliers than others. I mean, particularly of the methods I showed you, there is this density-based approach where low density points are actually discarded, right? So they are not integrated in a cluster. If you fit something like a Gaussian mixture, one approach is you could add a mixture component that is a very, very, very large uniform, and that should catch all the outliers. So, and I've done some work on this. So there are certain methods that are designed for dealing with this. Last one, please.
For these different clustering methods, I assume there's also kind of hyperparameters that you can specify for the models, such as the number of clusters or density penalization in the density model, which can also give like a range of different values or index scores for each one.
Indeed.
So when you're comparing them, would you kind of generate a range of scores for each clustering type, or would you kind of do some analysis first and then compare the different types?
Okay, so the question is, there are actually several cluster analysis methods that require some specification of some kind of hyperparameters. One of these is number of clusters. Another one is for example, the dbScan method has a size of a neighborhood for which the method is looking in order to make up these high density regions. And the question is whether I would actually go through several of these and compare them with this methodology. And my answer is that's a possibility. Sometimes I personally, I mean, really, to some extent, it depends on how much time you have and how many things you want to compare. Sometimes there are default choices of these. And one thing you need to realize, I have given some other presentations elsewhere about the number of clusters problem, is although there are methods to pretend you to estimate the number of clusters without requiring such specifications themselves, that's actually not true, right? If you think about two Gaussian populations and you put them closer and closer and closer and closer together, in most applications there is a certain point where they are so close you would rather treat them as one cluster than as two. And generally, a statistical formal method cannot know where the borderline is. Every method that works without such a specification makes a specification for you and you don't see it. And therefore, sometimes I think, instead of fixing something that you have to fix in order to estimate the number of clusters, you may well also fix the number of clusters. That's not the worst thing that you can do. So quite generally, I think this is a very subtle issue, and certainly you have the option to compare lots of things according to these statistics, but you also restrict yourself, and therefore, and sometimes you know, okay, I should be going for a low number of clusters, not for a high one, things like this.
Okay, so let's say.
Thanks a lot.